Hi, my name is Muhammad Imran Shah bin Abdul Hakim. So today we are going to talk about the synthesis and analysis of a quick return for bar linkage. So the mechanism selection and link specification. So the type synthesis is planar for bar crank rocker linkage selected. So it converts continuous rotary into oscillatory motion with quick return characteristics. So the number synthesis that four links plus four regular joints, that is frame, crank, coupler, and rocker. So from the design parameters, we can see that each links have a different length. So from here we can see the figure one, that is four bar crank rocker linkage mechanism with design parameters.
Hi, my name is Arun. Today we are analyzing our crank rocker mechanism. First, we calculated the quick return angle beta. As shown here, by using time ratio of 1.22, we determined that beta equals to 17.84. Next, we verified the Grashof criterion to ensure proper function. Referring here, we confirm that 17.68 plus 179.18 is lesser than or equals to 100 plus 126.82. Since this simplifies to 196.86 lesser than or equals to 226.82, the mechanism successfully passes the criteria.
My name is Deva. Now let us see the MATLAB kinematic analysis. This slide shows the position analysis and rocker angle plot of the quick return 4-bar linkage. On the left loop, closure equation and the Freidenstein equation, which are used to calculate rocker angle from the crack angle. On the right hand side, we can see the MATLAB result. From the MATLAB, we have obtained the desired theta, which is 1.22, and the desired angle, which is 29.97 degrees.
Hello, I'm Dimindran. We are building the performance verification for analysis. These are the quick return performance results. For the forward stroke, which is the slower motion, the crank rotates from 24 degrees to 232 degrees. The crank angle swept beta equals to 198 degrees. The maximum rocker angle is 90 degrees and the minimum rocker angle is 60.03 degrees. The return stroke, which is the faster motion, the crank rotates from 232 to 394 degrees and the crank angle swept alpha is 162 degrees. The time ratio calculation is beta over alpha, therefore we get 1.222 degrees, and the rocker oscillation angle is the maximum rocker angle minus the minimum rocker angle, therefore we get 29.97 degrees. These are the comparison with design targets. Both time ratio and rocker angle pass because both parameters are within the required plus minus 2% tolerance. The slight errors arise from rounding of link dimensions and MATLAB's finite angular step size. Therefore, the design successfully meets all quick return specifications.
Now I will explain the special point analysis of the rocker. We focus on the midpoint of the forward stroke. The forward stroke is from 34 degrees to 232 degrees, so the middle crank angle is 133 degrees. At this point, the rocker angle is 82.3 degrees and its angular velocity is 1.639 radians per second counterclockwise. For the rocker, both the instantaneous center and the acceleration pole are the fixed pivot O4, which is 100 millimeters. This is because O4 is fixed, so its velocity and acceleration are zero. Therefore, the rocker rotates at around O4.